Bismillahirrahmanirrahim. Assalamu alaikum, dear student. I am your physics instructor and I welcome you in Learn Physics by Hafiza Roj. And if you don't subscribe my channel, then first do it and click on bell icon so that my every new video will reach to you on time. Thank you. I will start with class 10th chapter 1 simple harmonic motion and waves. As we study in class 9th what is vibratory motion or oscillatory motion, and we know that to and fro or back and forth motion about a point is vibratory motion or oscillatory motion. Simply, it is the motion from rest point to the point which is located ahead and a point which is located back of the rest point is called vibratory motion or oscillatory motion. Simply, it is the motion about a point ahead and a back point. Other term we use for vibration is oscillation, and most famous type of vibratory or oscillatory motion is simple harmonic motion, which is also denoted by SHM. We will see what is simple harmonic motion. Simple harmonic motion occurs when the net force is directly proportional to the displacement from the mean position and is always directed towards the mean position. Let we say F be the net force and X be the displacement, and according to this definition F is directly proportional to the X, which is displacement from the mean position. And according to the definition of simple harmonic motion, this force is always directed towards the mean position. I will explain you what is vibratory motion. Suppose an object of mass m is initially at rest at position O, and we will disturb the object from position O to position B. It is the first step, and then we will release the object at point B. Then it automatically will move to the position O, and it will not stop here. It will move to position A, which is the third step, and here it will not stop. It will again move to position O, which is the fourth step, and this type of motion will repeat between A and B, and this type of motion is called vibratory motion or oscillatory motion. And the type of vibratory motion which is most important is simple harmonic motion, which we will deal in this chapter, and we will explain the different types of simple harmonic motion. There are two conditions of simple harmonic motion. Which motion we can say that this is simple harmonic motion? If net force or resultant force depends upon displacement, that means if we will increase the force, then displacement will also increase, and otherwise if we will decrease the force, then displacement will also decrease. In this way, force is directly related to displacement, and we call that force is directly proportional to displacement. And if we will increase one thing and other thing will decrease, opposite direction we will face, this will be indirectly proportional. But if one thing is increasing and other is also increasing, and if one is decreasing, other will also decreasing, this is the direct relation or directly proportional. According to this definition, one other important point is that force is vector quantity which has magnitude and direction, and we here also use vector quantity which is displacement. We do not use distance because distance is scalar quantity which has not direction. If we will use force which has direction, we will use displacement which has also direction. We will use both direction terms which are vector quantities. If we will use force which is vector and we will use distance which is scalar, it will not be adjustable. We have to use both vector quantities. And second condition is that this force will always be directed towards mean position or rest position. And there are three examples of simple harmonic motion which we will discuss in this chapter. First one is motion of mass attached to a spring on a horizontal frictionless surface, and second one is the motion of a ball placed in a bowl, and third example is the motion of a bob attached to a string. First we will explain example number 1. And there we have a spring whose one end is connected to wall or rigid thing and other end is connected to mass, and here we have mass whose one end is free and one is combined to spring. This is the arrangement of our system. And here is an object whose mass is m and which moves, and this motion we will said that this is simple harmonic motion because it fulfills the two conditions which are described in the definition of simple harmonic motion, and we will see how it fulfills the conditions of how it fulfills the conditions which are described in the definition of simple harmonic motion. That force is directly proportional to displacement, and that force always directed towards mean position or rest position. And other considerable thing in this example of simple harmonic motion is that we place this mass spring system on horizontal frictionless surface. The most important word is frictionless surface. Why frictionless surface we use? So that no friction, which means opposition, resistance, rukawat to the motion of mass, so that no opposition so that no opposition phase to the motion of the mass which is occurring through the simple harmonic motion. In figure A, we don't apply any disturbance or force on the spring. Due to this, force will act on the mass m due to spring will also be 0 and displacement also 0. And we know that everything wants to remain in its balanced state or in its original state. If spring length change, then it will exert force on the mass, so that this change will eliminate or finish and it will come to in free state or balanced state or in its original state. In figure A, there is shown the original spring, no change in its length, so there will be no force act on the mass due to this spring, and the resultant force is 0. And if we change the length of spring by increasing length, which is called stretched spring or expanded spring, which is related to increase in the length of the spring. In figure B, we displace the mass m from position O to position A, and spring covers displacement, not distance, displacement x. And now spring is not in balanced state or satisfying state and not feel satisfaction. So it will exert force on mass m that they come to position O and relax the spring. And we can see that the force is acting on the mass m and its direction is towards the position O. Here x is the displacement from position O, which is a rest position or initial position. We disturb the mass m from position O, which is initial position, and final position is at position A. And the displacement arrow indicates that the mass m is moving from position O to position A, and in this and direction is that the force will act on the mass m, but its direction will be towards the position O. We stretch the spring or increase the length of spring, and due to this there is a force which is acting on the mass m, and when spring is in its original state there is no force due to spring on the mass m, because there is no displacement in the spring. When there is a displacement there is a force, but we can see that there is an opposite direction. Displacement is from position O to A, and force is from position A to O. or there is an opposition or opposite direction. And other case in figure C is that we disturb the spring by compress, which means the spring length decrease, and again spring is not in relaxed state, it is disturbed now, and the spring covers displacement x again from position O to position B. And here again the mass m moves from position O to position B, and there is a decrease in the length of the spring as compared to original spring. We can see in the figure A, there is an original spring and the mass position is at point O, and in figure C mass moves from position O to position B, and the displacement arrow indicates that. And in this case there is also a force which is acting on mass m due to the spring, because spring wants to remain in its balanced state, or wants that mass m goes to position O and balance the spring. So due to spring there will be a force which is acting on mass m, and its direction is from B to O, because spring wants that mass m moves from B to O, but there is a displacement which is from O to B, and there is also opposite direction between displacement and force, but the distance between O to A and O to B is equal, and this is also the distance OB is also x, and distance OA is also x, and there is a condition in the definition of simple harmonic motion that the force direction will be always towards mean position, and we can see that the force direction in figure C is towards the position O, which is mean position or rest position. In figure B there is a stretched spring or increase in length of spring. There is a force direction also towards the position O. And we can say that this motion is simple harmonic motion due to the force direction is always towards the position O, and force is directly proportional to the displacement, which is F, and displacement is x, which means F varies with respect to x. F depends upon x. And we know that Hooke's law, which is about spring, says that the force which exert on mass m by spring is directly proportional to the change in length of spring. We say that this is x. According to Hooke's law, force is directly proportional to displacement. That means F is directly proportional to x, and we know that when we will eliminate or finish the directly proportional sign, there will be a constant and there will be an equal sign, and k is proportionality constant, and it is called spring constant, and there is a negative sign, and we want to from where this negative sign comes. There is an important question how negative sign comes, and we see from figure C that this force is always directed opposite to the displacement x. In figure B, the force direction is from A to O, but displacement direction is from O to A. There is an opposite direction between these two factors. And in figure C, the force direction is from B to O, but displacement direction, not distance, is direction from O to B. So there are opposite direction in these two cases, so there is a negative sign. And we want to define proportionality constant, which is K. It is called spring constant, and it is defined as, it measures the stiffness of the spring, which means hardness of spring. Hard spring large value of K, and soft spring small value of K. This is spring constant. And these are the mathematical steps. According to Hooke's law, we know that F equal to minus kx, and we can find k from this equation. K will be equal to minus F over x. And further we know that force equal to ma, and we will put this force in equation 1, and we get k is equal to minus ma over x. And we will find acceleration, where m is the mass of an object, F is the force, and a is the acceleration. We will find acceleration from k value, and it will be minus k over m into x. And we know k over m is a constant, because k is spring constant, proportionality constant, which is a constant, and mass m is constant, and constant divided by constant will give you a constant. So we can say that there is some constant which can be any value. We don't specify, only say that this is constant. And from this we know that a is directly proportional to minus x. Constant and equal sign is present in proportionality sign. This is the condition of simple harmonic motion for mass attached to a spring. So this shows that the mass m attached to a spring on a horizontal frictionless surface, so that no opposition, no resistance, no rukawat to the motion of mass. So this is the condition that this motion is simple harmonic motion. And now we want to define restoring force. A restoring force always pushes or pulls the object which is performing oscillatory motion or vibratory motion towards the mean position. It means this force always compel the object to move at the rest position or mean position. We see from figure B that there is a force acting on mass m due to spring from position A to O, which is always directed towards the mean position. And in figure C, there is a force which is acting on mass m due to spring towards mean position. And in these two cases, in one case this is pushing the spring, and in the other case pulling this spring, and directed always towards the mean position. And we can call this force is restoring force, because it compels the spring to restore the original position. We will explain how this is the motion of mass attached to a spring is an example of simple harmonic motion. We will see all. Initially the mass m is at rest at position O, called mean position, and resultant force or net force is 0, and displacement is also 0. In figure B, the mass m moves to position A and then released. This is the disturbance by us due to restoring force, which pushes or pulls the object towards the mean position, is exerted by spring on the mass, will move back the mass to position O. And we know that the vibratory motion or simple harmonic motion is to and fro motion about a point. We will discuss one case. Either it can be in figure B or it can be in figure C. Suppose we will explain in figure B case. Initially it is at rest at position O, and we will apply force on mass m, and it will move from position O to A, and due to restoring force which is exerted by spring on the mass, will move back the mass to the position O. First it is at rest at position O, then it will move by us by disturbing the mass by us to the position A, and we will release. It will move from position A to O, and at mean position O, which is rest position, the mass will not stop, rather it has maximum speed now at rest position. which means maximum or greater kinetic energy, because we know that kinetic energy is half mv square, which is directly related to velocity or speed. If speed or velocity will be greater value, then kinetic energy will also be greater value, which is related to the motion. So body or mass will not be stopped, rather due to inertia it will move to extreme position b. Hence at extreme position b the speed of mass is 0, which means zero kinetic energy. And when the mass goes on extreme position, the spring's length change and does not relax, so the restoring force will act on extreme position and will move mass to position o, and then moves at position o due to restoring force. This will be motion, which is simple harmonic motion, which obeys the mass attached to spring, which moves from O to B, and then moves from B to O, then O to A, and then A to O, and then O to B. This is simple harmonic motion which obeys the mass attached to spring, and the motion at fourth term is called one vibration. When we disturb the mass m, which is at position O, at the position B, and it will move to position again, it will move again to position O, and it will not be stopped here, rather due to inertia it will be maximum speed at position O, and it will move to position A, and here it is minimum speed, or we can say that zero speed. So it will not move ahead or further, it will move back. So at this point this is the limit of the object, so it will move back, and will move back due to restoring force of the spring, and it will move to position O, which is the fourth term. And at this point this is called one vibration. And we know about the energy, that energy cannot be created or destroyed, rather it converts one form into another form. That energy cannot be produced or disturbed, rather it converted from one form to another form. It converts from kinetic energy to potential energy to kinetic energy. It is the conversion between energy, and it cannot be produced or destroyed. And we say that at position O, where resultant force is 0, displacement 0, kinetic energy is maximum, because it has maximum speed, and kinetic energy is directly related to speed, which formula is that half mv square. And here potential energy is 0. Potential energy is related to position. There is mean position, rest position, not certain position. Kinetic energy is related to the motion. So here at this point there is kinetic energy and not potential energy. And at extreme position, in the positive x-axis it can be plus a, we can say any value, and in the negative x-axis it will be same value. I say that OA or OB distance will be equal, but with opposite sign, because it is positive x-axis and it is the negative x-axis. And at these two positions, which are extreme positions, here kinetic energies equal to 0, because no speed. Kinetic energy is half mv square. 0 speed mean kinetic energy 0, and potential energy here is maximum. Potential energy is due to the maximum displacement, because I say that potential energy is related to, we know the definition of potential energy, that potential energy is related to position. Some position means some displacement, maximum displacement, so it has maximum value. And kinetic energy, 0 speed, 0 kinetic energy, and at mean position O, kinetic energy is maximum due to motion, and potential energy is 0, because no specific position no distance covered, or we say that in the vector form that displacement is zero. Kinetic energy is maximum at the mean position O. So due to this factor that it has maximum velocity, so kinetic energy is maximum in this case, or in this system we form. Kinetic energy will be converted into potential energy, and potential energy will be converted into kinetic energy. But kinetic energy or potential energy, we can't say that it created or destroyed, rather it is the conversion between this system. We apply work, we do work from position O to position in B, from position O to position A, and we do work, and this work is converted into energy. We can't say that this energy is not produced, rather we apply the work, we do work on this system. It is the so this is the motion, and this work is converted into energy, and there is the conversion between energy, and due to this conversion, this is the whole system. And we know that the time period of simple harmonic motion of a mass m attached to a spring is given by the following equation. T is the time period where m is the mass which is attached to the spring, and k is spring constant. Time period is directly related to the mass m. If we will increase, the period will also be increased, and there is an indirect relation between spring constant, which is k, and time period. And we have to the information about time period. Time period is the time taken by the object to complete one vibration. I told you what is one vibration. In one vibration, time the object takes time is called time period, and time period is related to mass m and spring constant. This is an important question, that time period related to what things. This is related to mass m and spring constant, and 2 pi is a constant factor. Okay, thanks.